Hello, and welcome back to AP Environmental Science. Today I want to talk about the atmosphere, and I love this picture because it shows you how really tiny compared to the rest of the Earth that the atmosphere actually is. John Glenn said that if you took a globe that was 8 feet in diameter, that the atmosphere would be the thickness of the varnish on that globe. And so I think that we forget, because for us the atmosphere is so huge, but we forget that it's such a tiny, tiny part, mass-wise, compared to the rest of the system, the Earth and all the water and all of that. But I want to talk first about how we get this atmosphere that we have today. The early atmosphere was evil. I'm just kidding. It was bad for life, right? Conditions on the early Earth were not good for life. We had the sun blocked out by all sorts of particulate matter from all of this volcanic activity that's going on. It's about 30% as bright as it was today, probably. The atmosphere consists of methane and hydrogen, carbon dioxide, sulfur dioxide, water vapor, all of this. It's hot, right? There's acid rain. There's some liquid water, but most of it is gaseous. And so it's yucky, right, is kind of where I'm going with this. It's yuck. Now, here's your first question. Scientists believe that Earth's early atmosphere changed in composition as a result of which of the following things? Changes in the Earth's magnetic fields, the appearance of oxygen-producing organisms, the drifting of continents, a transfer of gases from the sun. Well, the reason that we have the atmosphere that we have, which is thick actually compared to other planets. So our atmosphere may be really thin compared to the Earth itself, but in terms of other planets, we have like the awesomest atmosphere ever. And we have one, which counts, right? There are other places that have no atmosphere. But changes in the Earth's magnetic fields, well, it's the magnetic fields that around the Earth that actually allow us to have the atmosphere to begin with, because they deflect the solar wind that has stripped the atmosphere off so many other places, right? Continents do drift, but that doesn't actually affect the atmosphere. It'll affect the climate of the continents, but that has nothing to do with the actual atmosphere itself. Transfer of gases from the sun, no, right? Just no. So what happens is we get oxygen-producing organisms. That is the answer. So, what we're saying here is that photosynthesis evolves. Cyanobacteria at some point evolved the ability to convert CO2 and water, right, in the presence of sunlight, to form glucose and oxygen around 3.5 to 3.8 billion years ago. And here's the equation that should look tremendously familiar to you. It is the summary of photosynthesis. And it is so successful, right, to be able to take these inorganic things and build organic molecules, right? Glucose in this case, a little energy storage situation. It's so successful that it actually becomes like the way for most autotrophs. And so you get a shift from these chemoautotrophs to these photoautotrophs. Now, the side product here is that you get lots and lots and lots of oxygen. So I have put in here these bold statements for several of these slides. The summary is photosynthesis in cyanobacteria is responsible for oxygen levels in the atmosphere today. Now, the other really big evolutionary event is that vascular plants evolve. About 450 million years ago, terrestrial plants, like modern terrestrial plants, evolve. And they are doing CO2 at this great rate, and they're doing photosynthesis. They're doing photosynthesis at this great rate, and they're taking CO2 out of the atmosphere. They're scrubbing the atmosphere. Now, when you have less CO2 in the atmosphere, right, you have a cooling effect, right? So we get global cooling, and so there are glaciers that start to form, and you start getting seasonal melt, right? And glaciers actually are responsible for a lot of the geography that we see today, because glaciers have carved out like lots and lots of the features that we have so familiar today. A lot of mountain, situation, the sharp edges to things, a lot of that's due to glaciation. Now, here's the other thing about vascular plants. They have roots, and roots go into rock, and they will break rock apart, and then you start getting soil, and you are having rain and you've got your soil and that makes mud, and so we start getting channelization of water through this mud, and you start to get actual bodies of water, rivers, right? And so it's the mud that allows for this to happen. And because you have new soil, you start to get the growth of actual trees, and that's the beginning of forests. As trees die, they will create dams, and that allows for flooding and deposition, and you get more great soil, more nutrient-rich stuff. It's awesome. So basically what we can say is that vascular plants are responsible for the reduction of CO2, which regulates temperatures, global temperatures, and they're responsible for the fertile soils that we find in all of the arable land around the world. So that brings us to the modern atmosphere, which is good for life. Yay! So when we look at the atmosphere, we have several levels, okay? We're going to start out with the thermosphere, like way out here, and then we have the mesosphere, and then we move to the two lower levels, which are the ones that we're concerned with, the stratosphere, okay, and the troposphere, okay? But we're going to start talking about the stratosphere first, because we want to talk about the ozone shield, yeah? The ozone shield is in the stratosphere. It is in the stratosphere. Ozone in the stratosphere, good. Ozone in the troposphere, bad. So what does the ozone layer do for us? It absorbs a lot of the UV that is coming from the sun, and so it protects us from overexposure by UV rays. Okay, and we know that UV causes cancer and stuff like that, which is bad. So ozone is produced naturally. First of all, we know that it absorbs solar radiation. We just talked about that. And when it absorbs solar radiation, oxygen, right, is going to break apart into its little free radical versions that are very reactive, and they're constantly looking for little friends. And so your free oxygen is going to bond with your diatomic oxygen, the oxygen gas molecule, and it makes ozone, right? So just the simple act of that whole area getting all of this UV is what helps generate more ozone, and that breaks down too, but mostly it just keeps regenerating because of all this UV. Now in the troposphere, lightning does the very same thing, actually, and so we do have ozone in the troposphere, but we're most concerned right in this part with the ozone in the stratosphere, which is good. Because if we didn't have the ozone layer, first of all, life wouldn't really have evolved anyway, because this would have been a horrible environment with lots of UV. And if we lose the ozone layer going forward, you can look forward to things like skin cancer, premature skin aging, eye damage, which can lead to cataracts and blindness. So that's bad. And it doesn't just affect people. I mean, UV kills cells. It's why we use UV lights to disinfect the goggles, right? It kills cells, and that is bad. So a side note, just for y'all that like to go tanning, whether it's in the sun or in a tanning bed, they both cause skin cancer and premature aging, so just keep that in mind. Now, let's talk about our interactions with stratospheric ozone. And that brings us to the conversation about the hole in the ozone layer, which is here over Antarctica. There is an ozone hole that's about 11 million square miles. This is not good, right? We just decided that having a depleted ozone shield is bad, yeah? So first of all, we need to ask, how does this happen, right? Ozone is very reactive, and it will react with other chemicals pretty strongly, including CFCs, which you may have heard of, which we'll talk about in a second. So ozone is broken down by a chlorine molecule, right? And then you end up in the end getting an oxygen gas molecule, right? And you know, you can make more ozone, but this process is actually a lot faster than the production of ozone from the free oxygen and the oxygen gas. And it's so much faster and so much more efficient that one chlorine molecule can actually destroy upwards of 100,000 ozone molecules. That is bad. So CFCs are actually responsible, ergo we are responsible, for the hole in the ozone. CFCs, chlorofluorocarbons, were developed in the 1940s and 50s. They serve as refrigerants, propellants, and fire retardants. Okay? By the 1970s, scientists actually started detecting CFCs in the upper atmosphere, mainly in the southern polar region, right, the South Pole. And that is because, first of all, the CFCs are moved into the upper atmosphere by air currents, but as they cycle through, you can see this very interesting air pattern sets up here over Antarctica. Because there is a little circumpolar ocean current around Antarctica, it traps all of the wind patterns here, and it creates this big circular wind, and it's a little bit like a gyre. It just dumps everything out right here. That ocean current is also responsible for the extremely cold temperatures. Antarctica is much colder than the Arctic, okay, and it's because of that ocean current around that continent there. And so unfortunately, this sets up the perfect environment for the depletion of ozone, because what you need for that is cold temperatures, lots of chlorine, CFCs, and lots of sunlight. And you get 6 months out of the year is all sunlight there. So that is the place where you're going to have it, okay? Now, the CFCs, right? Breaking up the ozone, harmful ultraviolet rays coming in. This is exactly what I said, but it's a nice little picture for you to have, because I know we like pictures sometimes. Okay, so what? Well, you've got an increase in skin cancers, both in animals and plants. You also have necrosis, animals and humans. You get necrosis in plants, right? Because there's an inhibition to some plant life, and that means that you have weaker plants. They're more susceptible to pests. They don't grow as well. And this is going to endanger not only terrestrial ecosystems, but also crops. And you also have a reduction in the growth of phytoplankton. This is the photoautotroph group that produces the oxygen out of the ocean and is the basis of the aquatic food chain. And remember, it is the oceans. The oceans produce more oxygen than anything else, including the rainforests, right? The tropical rainforests, because the tropical rainforests are the big oxygen producers, but the ocean, phytoplankton in the ocean produces more oxygen. So this is leading to bad things. Now, on the plus side, right, we as a global community got together and everybody signed something called the Montreal Protocol. This was an international agreement to phase out CFCs, and it's been revised several times, right? But developed countries basically phased CFCs out by 1996, and they went to a less destructive alternate, right? It's more ozone friendly, so that we moved to HCFCs. And developing countries were supposed to phase out all of their CFCs by 2005. So, you know, that hasn't happened entirely, but for the most part, most countries have actually phased out CFCs entirely, okay? And halons are another thing that have chlorine in them, but CFCs and halons, the Montreal Protocol was about that, but CFCs are the ones that I want you to know, okay? And as a matter of fact, when you start looking at that phasing out, here's where the Montreal Protocol is signed, and boom, there is a rapid decrease over a decade. So we can actually make changes, right? We can make changes when we want to. Now, here's another really good question. If we take immediate action to stop using all ozone depleting chemicals just in general, models indicate it'll take about 60 years for the ozone layer to return to 1980 levels. This would be, you know, before the hole got bigger. The answer to that is actually true, okay? Just because you stop doing something right now doesn't mean that the effect is going to be right now. And just because you start doing something right now doesn't mean the effect is going to be right now. Okay? Ozone depletion, because of the persistence in the atmosphere, is going to continue to increase, right? Far past the time that we actually phased out CFCs. And it's starting right now to recover, but it's going to be mid-century before it goes back to what it was before all the CFCs. And so that's something that you have to realize, is that things in the atmosphere when you're dealing with large systems are not immediate. Okay, so now let's talk about a new thing, the greenhouse effect. So we're kind of hitting the major topics of the environment. Now we're going to talk about global climate change a different day. So today is really just about the greenhouse effect and how it affects like us now and the atmosphere and all that good stuff. Okay, so the first thing, the phenomenon causing the greenhouse effect is that what in the lower atmosphere selectively absorbs re-radiated what? Well, we know carbon dioxide is a greenhouse gas, so obviously the answers need to have carbon dioxide. But there are other greenhouse gases too, right? Ozone actually is greenhouse gas, for instance. But carbon dioxide, methane, water vapor, nitrogen oxides, all of those gases in the lower atmosphere absorb re-radiated infrared radiation. The answer here is 2. Okay, so that's what you need to know. So incoming incident solar radiation comes in, and it is re-radiated by the Earth. That is absorbed by the carbon dioxide, methane, and other greenhouse gases. And here is a picture of what I'm talking about. Incident solar radiation, okay? Some of it is reflected right off the top of the atmosphere. Some of it's reflected off the surface of the Earth. Some of it is absorbed. And anytime you absorb electromagnetic radiation, it is going to be re-emitted at a lower level, okay? Less energy, right? And so that is going to go from visible light and UV to infrared radiation, okay? And then that's trapped in the atmosphere. Some of it goes out, but some of it's trapped. And this is why we have the nice, warm, yummy atmosphere that we have that gives us liquid water, which we need for life. Yay. So here's just another picture. And this tells you actually that there are 3 factors that really affect the climate, global temperatures, things like that. And the first factor is how much energy are we actually getting from the sun? Okay, that's a big one. The second one is going to be what's in the atmosphere. That's going to be all your greenhouse gases and all that good stuff. If greenhouse gases increase, it has the ability to absorb more infrared radiation. Okay. The other thing that we want to look at, the last thing, is albedo. Okay, and we'll continue to talk about chemistry of the atmosphere as we talk about global climate change. But I want to talk about albedo right now. Okay, albedo is reflectivity. Different surfaces have different colors, right? And those colors will reflect light differently. So obviously things that are whiter, are lighter, are going to have a higher albedo than things that are darker, right? So asphalt, which is the dark pavement, is going to be about 5 to 10% reflectivity. That means it's going to absorb 90 to 95% of the light that falls on it, right? Fresh snow, on the other hand, right, is going to be 80 to 85% reflective. Yeah, so the albedo is 80%. Yeah, and so that means that it's going to be less absorbed, less infrared, right? So ice is a really good thing to have if you want to have cooler climate, right? Dark things are less, okay? And so here's an example. If 85% of the light is reflected off the surface of ice, well, that's super duper, right? Then you're only absorbing 15%. But in places where there's not ice, then you're going to absorb, say, 90 to 95%. In this case, we have 93%, which means only 7% is reflected back out into space, and the rest of it is available to heat up the Earth. I want you to remember this because this is going to be something that we're going to talk about a little bit later. Okay, and so here's albedo. This is just some more information on the difference between like soil, snow, open ocean. This also has how things have changed. We're going to talk about Greenland later on, but as the ice sheet melts on Greenland, how that's changing the albedo. Okay, now I want to talk a little bit more about things that go into the atmosphere. So we had reflectivity, but here we're going to go back to that whole chemistry thing, right? Volcanoes, huge impact on the environment if you have a really big volcanic eruption, right? Because you can see, and I think this picture is spectacular. You have all this particulate and all these hot gases and all this stuff coming out of this volcano, and it is intense enough and has all of this energy and all this motion that it actually creates its own storm, right? And so here this is lightning that's in the effluent coming out of the volcano. But what that does is you get this cloud cover, right? And clouds actually make a difference to what's absorbed and what's not absorbed. High clouds are going to trap a lot of heat, right? Whereas low clouds are going to be more reflective. They have a higher albedo, and so high clouds can contribute to warming, but low clouds contribute to cooling. And volcanoes make thick, low clouds, and so they're actually a cooling mechanism, okay? Now, the downside is that you get some acid rain situations with it because you get the sulfur dioxide that's coming out of the volcano. You've got hydrogen chloride, which will form hydrochloric acid in the water. So you may get cooling, but you also get acid rain. Yeah. And you've got this great amount of ash that's coming out that gives you particulate pollution. So it's not just acid rain there. The ash itself is an actual pollutant. So anyway, but volcanoes lead to cooling. Now, obviously, the answer to global climate change is not to, have lots of volcanic eruptions. But interesting thing, we think that one of the mass extinctions actually was caused by the eruption of the Siberian traps. The Permian extinction was caused by the eruption of the Siberian traps, which caused global cooling because you had such a massive volcanic eruption. Okay, kind of situation, lots of volcanoes. All right. So if it's not just volcanoes, though, what if it's also any particulates that are in the atmosphere? So other things will have a cooling effect too, as long as they form low clouds. So dust storms, which is a natural thing, but then also fires, which can be natural or anthropogenic, and then the water vapor or sometimes actual pollutants that form clouds coming out of factories and things also can contribute to global cooling. Okay, it's not enough to offset global climate change, global warming, yeah? Okay, so let's just look at this in terms of volcanoes and all that good stuff. How would the eruption of a volcano not affect the global climate? Dust from the volcano blocks sunlight. It releases CO2, which is a greenhouse gas. Released hydrogen chloride and sulfur aerosols can cause stratospheric ozone depletion, allowing increased ultraviolet light to reach the Earth's surface. Sulfur aerosols increase the amount of radiation reflected back into space, or all of these affect the global climate. Well, sulfur and hydrogen chloride don't do stratospheric ozone depletion from volcanoes, right? And so, I mean, there is some with the hydrogen chloride, but not really, and definitely not with the sulfur. But here's the catch on that one. That's not the problem with statement number 3, right? Statement number 3, the problem is about ultraviolet light reaching the Earth's surface. And here is where we want to say, ultraviolet light does not contribute to global climate change. The hole in the ozone layer, that increased UV, is not related to global warming, global climate change. Those two things are not, no samey. They are not the same. They are not related. So if anybody says, hey, there's a hole in the ozone and that makes global climate change, you can say to them, wow, that is crazy talk, and you should never say that because it's totally wrong. Yeah. So no ultraviolet light in terms of global climate. So let's boil it all down. What affects climate? The Earth and Sun geometry, so solar output. We talked a little bit about solar output, but also like how far away the sun is and all that good stuff. That affects it. The atmospheric factors are going to be albedo and atmospheric chemistry. Then surface factors, land and ocean factors, are going to be albedo again, right? And then the surface atmosphere exchange, which we'll talk about later on. And then you have some tectonic factors, volcanic emissions we talked about. And then, of course, just continental drift. Where are the continents in relation to the solar radiation? Which brings us to our next question. The sun's rays strike the Earth most directly at the equator or the poles? Well, it's the equator, right? So if you are closer to the equator, you're going to have a warmer climate, okay? Now remember that 0 degrees latitude is the equator, but the actual place where the solar radiation is highest is going to kind of depend on where we are in relation to the sun, because we have that whole axis tilt thing, which we're not talking about now, but keep in mind, and that's what causes this kind of shift situation here, okay? Now, the thing about this uneven heating is that it drives convection currents in the atmosphere. So if you look at the equatorial regions as being a warm surface, then there's going to be a lot of evaporation, right? Because there's a lot of heating, and so you get a nice low pressure, right? The air rises because it's expanding and it's warmer, and it's going to go up and it's going to hit the top of the troposphere, right? The bottom of the stratosphere. And so it's going to split, and then it's going to skate along the bottom of the stratosphere. But as it does that, it's a lot cooler, and so it's going to be cooling down. It's going to become more dense. It's going to fall, right? And it's a cooler surface here. It is going to cause a high pressure system here, and then it's going to hit the actual surface of the Earth, and that falling air is going to split. That's one of the things that creates wind, which we'll talk about in just a second. And then it's going to travel back towards the equator, making this convection current, or it's going to travel north, making another convection current. Again, we'll talk about this later. But here is a convection current cell in the atmosphere, okay? And if you want to start throwing in things like clouds and the sun and the ocean, it looks a little bit like this. Equatorial region. Evaporation, right? Heat, okay, so the air is expanding. It's rising, it's humid because it's warm and there's all that evaporation. As it reaches higher in the atmosphere, it's going to start to cool off. It's going to condense into clouds. That water is going to fall out in the form of precipitation. This air is going to move. It's eventually going to rain out, and you're going to have cool, dry air sinking. It's going to warm up as it hits the surface. There's going to be a high pressure system here, and it's going to be really dry, warm air. Warm, humid, lots of rain. Dry, not lots of rain. That is an interesting thing. And actually what we're talking about here is the setting up of the atmospheric cells, right? The circulation cells. So here at the equator, we have that first system that I was talking about. The warm, right, less dense air rising. All the clouds, all the rain. Hey, that's where all the rainforests are. What a coincidence. Reach the top of the troposphere, going to split right in two directions, so you get two cells, one to the south, one to the north, and that air is going to fall. Now, as that air falls, right here, it's going to split, and some of it's going to go back to the equator, some of it's going to go north and begin the feral cell, or the mid-latitudes, okay, the mid-latitudinal cell. And that's going to do the same thing. You've got rising, so you're going to have cooler up here, but it's going to be raining, right? Here was hot and dry, cooler and raining, cold and dry, right, for the polar cell, okay? If you have questions about this, please ask in class. Now, because you have this air that's this kind of vertical system, you get these perpendicular winds, and so these are high-speed currents that are in the air flowing perpendicular to the atmospheric cells, and they are called the jets. And this one is the one that you might be most familiar with. It is the polar jet, right? It's the jet stream that they talk about on the weather when we talk about the jet stream moving north and south, right? That's it. And it's created by these other convection cells. Very exciting stuff. Okay, so here's a fun history question. When ships were powered by sails rather than engines, they tended to follow the trade winds and avoid sailing along the equator. The best explanation for this is there's too much precipitation along the equator. The places that ships' crews wanted to go were closer to the trade winds than to the equator. The prevailing direction for the movement of air masses along the equator is upward, which would not propel a ship. There are too many superstitions associated with the equator, and wind direction is too unpredictable, so ships would follow any path the crew could find. There is a lot of precipitation along the equator, but I mean, you're in a boat. You're already dealing with water, so who cares, right? Places, sailors are going all over, right? Let's look at the bottom one. Wind is too unpredictable. Actually, it's very predictable. Sailors are some of the most superstitious people on the planet, so that's just kind of, whatever. Not the answer to the question, though. And then if you're talking about air rising, number 3, right? Air is rising at the equator because that's where you have all that incident solar radiation. And so you actually have the air movement up. And so you get the doldrums, right? That you never wanted to be in. This is where your ship is what they like to call becalmed. And you just sit around. This is also where the idea of cabin fever comes from, because you get stuck, it's hot, you're stuck in the cabin, you're not going anywhere, you don't really know if you're going to pick up winds at some point. Hopefully you'll drift into the trade winds and get pushed somewhere, and that'd be great, but maybe not, this makes you a little stir crazy. So when you put that all together, you can see here are the atmospheric cells. Here is that one of the jet streams. Here's the other jet stream. Hadley cells, feral cells, or mid-latitude cells. Polar cells, these are the polar easterly winds. These are the westerly winds. These are the ones that push our currents here. These are the trade winds, right? And you can see it's repeated in the southern hemisphere. And it's a very predictable pattern, okay? Very predictable pattern. All right. Now, large regions of northern Canada and Russia are covered in these huge boreal forests, these huge coniferous trees. That's like pine trees and stuff. These regions are in the interior of continents. These regions are close to the North Pole. The forests formed long ago but have not died off yet. Rising air currents tend to drop their moisture over these regions, or all of the above. It's not 5. Some of the regions are interior, some of them are on the coast, right? They're not really that close to the North Pole, and that's good because that's a desert. The forests are there. 3 is just dumb. Rising air currents, though, remember, you're taking all that moist air, and as you go up, it's cooling off and condensing and raining. So that phenomenon that's occurring to make those tropical rainforests around the equator, the very same kind of phenomenon is occurring in northern Canada and Russia with the boreal forests, because that's that other split between the cells. And this sets up a whole climate system. So you start out at the equator with your big forests. By the time you get to about 30 degrees, that's that dry air sinking, and so you are in the desert. And in between, you get grasslands and shrublands and deciduous forests. Same thing as you go from the desert to the big boreal forests, you get shrublands and grasslands, right? And deciduous forests. And then you do the same thing from 60 to 90, and then you have a desert. So you've got hot deserts at 30, you have cold deserts at 90, right? You have temperate rainforests, essentially, at 60 degrees, and you have tropical rainforests at 0 degrees, okay? Now, the very last thing, I know these have been long, but the very last thing I want to talk about is something else that's going to affect the climate of local areas, and that is the rain shadow effect. So we've seen these big systems that create these biomes, but another thing can happen, and that is the interaction of the wind coming off of the ocean with mountains, right? And so if you think about the United States, for instance, you have the Rocky Mountains and the Sierra Nevadas and the Cascades and all that good stuff. Well, as the wind comes off the Pacific Ocean, it's going to go up those mountains. And if you look at most continents, actually, if they have mountains on the edges, the interior, at least part of it, is going to be desert, right? Because what happens is this nice moist air off the water goes up the mountain, and it's cooling and condensing, and so eventually it's going to rain out, right? And so by the time the winds actually go up and over the mountain, they've lost all of their moisture because they've been pushed up so high in the atmosphere. This is called the rain shadow effect, and on the other side you will have drier or really dry, arid lands creating deserts. Okay, you can also see it in Chile, for instance, with the Atacama Desert. It hasn't rained there in, like, I don't know, 11 million years or something ridiculous. And that's because the Andes are so high. Yeah, so same idea. Okay, that is it. We had a lot of information in a fairly short period of time. So if you have any questions, please let me know, and I will see you next time in class. All right, thanks for listening.